Hello everyone. In the previous videos we were discussing the compactness of a set. Now in this video we are going to discuss some more theorems of the related to the compactness of the set. And the first theorem is if F is closed and K is compact then F intersection K is compact. The proof is very easy, since we know that compact subsets of a metric space are closed. This implies we can say that since K is compact, so K is closed. This implies K is closed. And also, since F intersection K is the F intersection, it is an intersection of two closed subsets, so F intersection K is also closed. And since F intersection K is a subset of K where K is compact set, so we also know that closed subset of a compact set is compact. F intersection K is closed and K is compact, so F intersection K is also compact. This implies F intersection K is compact. Hence proved. Another theorem, theorem number 2. If E is an infinite subset of a compact set K, then E has a limit point in K. The statement is, if E is an infinite subset of a compact set K, then E has a limit point in K. Suppose this is K and there is a subset, infinite subset E, infinite subset. Proof: suppose if possible no point of K were a limit point of E. Limit point of E. Then each Q in K, each Q in K would have a neighborhood VQ which contains at most one point of E if Q belongs to E. Suppose Q belongs here in E, then Q will be the only point of E in VQ, because we assume that it has no limit point. Then this implies for each K, for any point Q in K, it would have a neighborhood VQ which contains at most only one point. Suppose the point is Q, then Q will be the only point. There is no another point which belongs to this interval, this neighborhood. This implies no finite subcollection of V alpha can cover K, and the same is true for E. Since E belongs to K, E is a subset of K. This contradicts, because E is infinite. So this contradicts the fact that E is infinite. This contradicts the compactness of K. This implies our assumption is wrong. Our assumption was there is no point of K over the limit point. That means our assumption is wrong. So E is an infinite subset of a compact set, then E has a limit point in K, hence proved. Now the next theorem is theorem number 3. If the interval IM is a sequence of intervals in R, or you can say R1, such that IN contained IN plus 1 or IN plus 1 contained in IN, where N from 1 to up to, then intersection N from 1 to infinity IN is not empty. This is one of the most important theorem. If IN is the interval denoted by A and Bn, bounded by A and Bn and the closed interval, and let E be the set of all ANs, these ANs. Then E is non-empty and bounded also, bounded above by B1. Suppose it is this is the real line R1 and this is the intervals A1, B1, A2, B2, A3, B3 and so on, and the collection of all AIs A1, A2, A3 is called E. And it is bounded by B1. No AIs is greater than B1. Now let X is a supremum of E. It must have supremum. If M and N are positive integers, then AN is less than or equal to AM plus N is less than or equal to BM plus N is less than or equal to BM. We can see that from this figure. We can also understand the thing. So that X is less than or equal to BM for each M. Since it is obvious that AM is less than or equal to X, because X is a supremum of E. So AM is always less than or equal to this supremum X. This implies X belongs to IM, M from 1 to hence N from 1 to infinity, IN is not empty. We get X is not empty. Hence proved QED. Next theorem, theorem number 4. Every K cell is compact. Now the proof. Let I be a K cell. This implies X belongs to I and X is like X1, X2, Xk, because X belongs to I and I be the K cell. What is one cell? One cell is R1. Two cell means R2. We have A1, B1. This element belongs to R2, two cell. Similarly, we can understand what is K cell, such that AJ is less than or equal to XJ is less than or equal to BJ, where j is from greater than or equal to 1 and less than or equal to k. Now put delta is a distance, and the distance is just like summation j is from 1 to k bj minus aj whole square to the whole power 1 by 2. Then mod x minus y is always less than or equal to delta. It is, suppose we have a R2 2 cell and we have a square or rectangle, so the difference is delta. So always, suppose it is x, y, z, t, difference between x and y is always less than this delta. This difference is always less than delta. So x minus y is less than or equal to delta if x belongs to I and y belongs to I. And suppose in 3D suppose there is a cuboid, so the difference between this and this we consider it delta. So the every difference is always less than delta. Now suppose, if possible, there exists an open cover G alpha, open covers G alpha of I, which contains no finite subcover of I, because we are going to prove every k cell is compact. Now we are going to prove by the contradiction. So suppose if possible it is not compact, that means the cover does not contain the finite subcovers. That means I cannot be covered by the finite subcovers of this open cover. Now take Cj is equal to Aj plus Bj by 2. Suppose in two cell we have a rectangle and the coordinates are A1 B1, A2 B2, A3 B3, A4 B4. Now what we are doing, we are just A1 plus B1 by 2. We are just doing this. This is what A1 C1 is A1 plus B1 by 2, A2 plus B2 by 2. So A1 plus B1 by 2, that means we are just partition this one cell into the 4 cells. The intervals AJ CJ and CJ BJ. Suppose we have this C1, so the interval is A1, this interval A1 C1, C1 B1, and then determine 2 to the power k cells. 2 to the power k cells. K is equal to 2. For k is equal to 2, we have 2 to the power 2. 2 to the power 2 means 4. We have 4 cells. 4 k cells. So 4, we have 4 2 cells. We have 4 cells. 1 2 3 4. 2 to the power k cells, whose union is I. Now at least one of these sets, and we call it I1. Suppose it is I1. We call it I1. Cannot be covered by any finite subcollection of G alpha, because we assume that it is not compact. So, and suppose I is the part that cannot be covered by the finite subcollections or subcovers, because otherwise I could be covered. So I is proved as a compact, and we are actually in the process to prove it compact. So it is not covered by the any finite subcovers. Now next, subdivision or subdivide I1 and continue this process. We obtained a sequence IN with the following properties. Number 1, I1 contained I1 contain I2 contain, and so on. Number 2, IN is not covered by any finite subcovers. Of G alpha. Number 3, if X belongs to IN and Y belongs to IN, then X mod of X minus Y is always less than or equal to 1/2 to the power n into delta, or we can write 2 to the power minus n into delta. By 1, we know that, and also we know that IN is contained in IN plus 1, n is equal to 1, 2 and so on. Then intersection I from 1 to infinity, IN is not phi. We have seen in the previous theorem. This implies let X star belongs to In which lies in every In because it is in the intersection. For some alpha and X star in G alpha, for some alpha X star in G alpha, since G alpha is open, this implies X star is interior point. This implies there exists a neighborhood of X star with the radius r greater than 0, suppose, such that mod of y minus X star is always less than r. This implies y belongs to G alpha. If n is so large, then 2 to the power minus n delta is less than r. Then by third property, In is contained in G alpha. This implies In is covered by G alpha, that is a single open cover. This implies, which contradicts the second, that is In is not covered by any finite subcovers of G alpha, but here we can see that In is covered by the single cover G alpha. This implies our assumption is wrong. Because of this contradiction, we can say that I is compact. Hence proved. Now we have a definition of perfect set. Perfect set. A set E is perfect if E is closed and if every point of E is a limit point of E. A set is called perfect if E is closed and every point of E is a limit point of E. Now we have a theorem. A non-empty perfect set is uncountable. The proof is, suppose if possible, perfect set P is countable. This implies there exists a 1102 function, there exists a bijection from N to P. That means there exists a correspondence from set of natural number to the set P, because it is countable. So we can enumerate the elements of P as P is a set containing the element x1, x2 and so on. This is countable set, and we will prove it is uncountable by the contradiction. That is, the set is, if we have a bijection 1-1 correspondence, or there is a correspondence 1-1 correspondence, that means every element of P appears in this list. Let I1 be the closed interval that contains a point x1 in its interior since P is perfect. The element x1 is not isolated by the definition of the perfect set. It must be a limit point, so it is not an isolated point. So there is some other element y2 of P or in P such that y2 is also in the interior of I1. Now choose a closed interval I2 centered on y2 so that I2 is contained in I1 and x1 does not belongs to I2. Suppose we have I1, this interval, and we have a point x1. Now we have another point y2, which contain in I2, and x1 is here, not in I2. This is I2. Similarly, we can find another point y3 in I3, and y3 is not in I2. Now, since y2 is contained in I2 and y2 is in P, This implies I2 intersection P is not phi. So the element Y2 in P is not isolated point. So there exists Y3 in P, that is in the center, that is in the interior of I2, and we may choose Y3 is not X2. Y3 is different from X2, because if Y3 is equal to X2, then we can choose, and we have another choice of Y3, because it is not a Y2 is not an isolated point, so there must be another point which is different from X2. Then choose I3 in I2 centered at Y3, for which X2 is not contained in I3, and the intersection of I3 and P is not phi, with the same reason, since Y3 is in I3 and P also. So the carrying out this construction inductively results in the sequence of closed interval In satisfying number 1, In plus 1 is contained in In, number 2, Xn is not contained in In plus 1, and number 3, In intersection P is not phi. So for each n belongs to the set of natural number, the set Kn is equal to In intersection P is compact, because In is bounded and In intersection P is closed. This implies intersection n from 1 to infinity Kn is not phi. On the other hand, since Kn is contained in P and Xn is not contained In plus 1, for every n belongs to set of natural number, this implies the intersection n from 1 to infinity Kn is phi. This is the contradiction. This is the contradiction that implies that P is uncountable. Suppose we have x3. From here we can see that it does not belongs to I4. x2 does not belongs to I3, and similarly we can see that the intersection of all kns is phi, null. So this is a contradiction, so we can say that our assumption was wrong. This implies the P is uncountable. Hence proved. Now we have another definition: connected set. Two sets A and B of a metric space X are said to be separated if both A intersection the closure of B and closure of A intersection B are empty, and a set E is said to be connected if E is not a union of two non-empty separated sets. And from here we can see that if A intersection B closure and A closure intersection B are empty both, then we can say that the sets are separated. So we can also observe that if the sets are separated, then we can say that they are disjoint also, but the converse need not to be true because of this closure. Neither A, neither B, nor the set of all the limit points, that means the drive sets, intersect each other. That means suppose we have A, this is A, and this is the closure of B, this is B, and this is the closure of B, this is B, and this is the closure of B, but they does not intersect each other. That means the intersection of A and the closure of B is phi. So it is clear that the disjoint sets are separated, but the separated sets are need not to be disjoint. Now we have a theorem. A subset E of the real line is connected if and only if it has the following property: if X belongs to E and Y belongs to E and Z lie between X and Y, then Z belongs to E. Or we can say that the subset E of real line is not connected if the following property is not satisfied. Now the proof of the theorem. If there exists X in E and Y in E, and some point Z in the open interval X and Y, such that Z does not belongs to E, then E is equal to AZ union BZ, where AZ AZ is E intersection minus infinity to Z, and BZ denotes E intersection Z to infinity. Suppose we have a line R and Z is here. Suppose Z is here and this is Y and that is Z, that is X. So AZ is intersection of E and minus infinity. This is minus infinity and here we have infinity, minus infinity to Z. This is AZ and not AZ, actually AZ is here. BZ and AZ BZ are, and suppose it is E, this is E. So AZ is E intersection minus infinity to Z. This is E, this complete line, this is E, but not here. That means E is not, Z is not in E. Suppose we have E intersection this open interval minus infinity to Z. This is nothing but AZ, this is AZ, and here we can see that this is BZ. BZ is in E intersection Z to infinity, this open interval Z to infinity. And what is E? E is here, this point is Z, and Z does not belongs to E. X and Y belongs to E. So this is E and this is E, but this point is absent from E. This is E, or we can say that X to Z union Z to Y. This is E, and Z is outside of this interval E. This is nothing but this AZ union BZ. Now since X belongs to A and Y belongs to B, and A and B are non-empty, because X belongs to A and Y belongs to B, so A and B are non-empty. Since AZ is a proper subset of minus infinity to Z, and BZ is a proper subset of Z to infinity, and they are separated. Hence E, that is E is AZ union BZ is not connected. So what we have proved? We have proved if this property does not satisfy, then the subset E is not connected. That we have proved. Now conversely, suppose E is not connected, Then there are non-empty separated sets A and B such that E is equal to A union B, because E is not connected. So it can be written as a union of two separated sets. From the definition of the connected set we can see very easily. Then pick 2 points x from A, y from B, and assume that x is less than y. Now define z is equal to supremum of A intersection x comma y, close interval x comma y. Now from the theorem we have discussed in the previous videos, and the theorem is, let E be a non-empty set of real numbers which is bounded above, and let y is equal to the supremum of E, then y is contained in the closure of E. So by using this theorem we can see that Z belongs to the closure of A, and hence Z does not belongs to B. In particular, x is less than or equal to z is less than y, because x is less than y, and suppose x lie between x and y, so z may be x or greater than x. If z does not belongs to A, this implies x is less than z is less than y, and z does not belongs to E. So the condition does not satisfy if the set is not connected, as we assumed E is not connected, so the property does not satisfy. Now if z belongs to A, then what happen? Then z does not belongs to the B closure, hence there exists a point z1 such that z is less than z1 is less than y, and z1 does not belongs to B. Then we can see that z1 lie between x and y, and z1 does not belongs to E. Again we can see that if z belongs to A, then again we have a point which does not satisfy the following property. Hence proved, if the property does not satisfy, then the set is not connected, and if the set is not connected, then the property does not satisfy. Hence prove the theorem.